Hi everyone, this is part one of our material on cryptography. Previously in our course, we've discussed coding for efficiency, for instance, minimizing average code word lengths and data compression. We've also discussed coding for reliability, which involves sending messages through channels, error correction, linear codes, perfect codes, and things of that nature. So now we're going to shift gears and discuss coding for secrecy. This is otherwise known as cryptography. So the word cryptography has two parts. So crypto means secret, and the graphy part means writing. So secret writing. Before we can turn our attention to cryptography, we need to address some matters of arithmetic. Now, you might remember from our discussion of error-correcting codes that finite arithmetic was very important. In fact, this allowed us to develop the notion of a linear code, which helped us automate a lot of facets of error correction and determining whether a string is a code word and things of that nature. So you might remember from the linear code stuff that all of the arithmetic was based on this finite arithmetic on the set F2 consisting of just 0 and 1, right? So we could add 0 to itself to get 0, 0 plus 1 and 1 plus 0 are both equal to 1, and then 1 plus 1 is equal to 0. And similarly, we had a multiplication operation. So we can extend that idea to an arithmetic on this set that we call z sub n. So z sub n, we first start with a value of n. Z sub n consists of the numbers 0, 1, up through n minus 1. And then we can add and multiply numbers in Zn by just adding and multiplying them as if they were ordinary integers, and then computing the remainder upon division by n. So this arithmetic that I'm describing on Zn, if n is equal to 2, then you wind up with this exact arithmetic that we considered when we were talking about linear codes. Okay, so we have a few examples here to get us familiar with the idea of these finite arithmetics. So the very first thing we want to do is compute some things. We're going to compute 3 times 5 plus 1 in Z8 and in Z9. Okay, so what is Z8, for instance? Well, according to our definition, it's just these symbols 0, 1, 2, 3, 4, 5, 6, and 7. And now if I'm going to compute 3 times 5 plus 1 in Z8, well, first I compute that as if I'm computing in the ordinary integers. That is, I take 3 times 5 to get 15, and then I add 1 to get 16. And then what I do is I divide that result, 16 by 8, and then I ask myself, well, what is the remainder upon computing that division? And the remainder is 0, right? So 3 times 5 plus 1 is equal to 0 in Z8. Okay, now let's consider this same computation, but instead of working in Z8, let's now suppose we're working in Z9. So now we're going to consider Z9. And now Z9 consists of the symbols 0, 1, 2, up through 8. And to make this computation, I take 3 times 5 plus 1, which again is 16. But now I'm going to divide 16 by 9 and compute the remainder. So the remainder there is 7, right? So 3 times 5 plus 1 is equal to 7 in Z9. All right, now there are various inverses, additive inverses and multiplicative inverses that we need to discuss inside of Zn. So if we, first for additive inverses, if we start with an element A in Zn, then minus A is the element of Zn where if you take a and add it to minus a, you get 0. So we're going to make some computations of additive inverses inside of Z13. So the first question is, what is minus 2 inside of Z13? And, to answer that question, we need to know, well, what number do we add to 2 in order to get 0 inside of Z13? So remember, 0 corresponds to sort of any multiple of 13. And so really the only way you can fill this box is to put in 11, right? 2 plus 11 is 13. Divide 13 by 13, it goes in one time with a remainder of 0. So minus 2 is equal to 11 in Z13. Now you might pause the video and see if you can figure out what minus 8 is in Z13. That is, what number in Z13 would you add to 8 in order to get 0? So now maybe you've gone away and you've thought about that for a little bit. So minus 8 is going to be 5 in Z13, because when I take 8 plus 5, I get 0. I get 13, which is equal to 0 inside of Z13. All right, so this idea of additive inverse, there's an analogous idea for multiplicative inverses. So before we go on to multiplicative inverses, let me add something, no pun intended, about these additive inverses. Every single number in Zn, right? If I give you a Zn and I ask you to pick any number in Zn, it will always have an additive inverse. Okay, now let's go talk about multiplicative inverses. So if we start with a number in Zn, then A inverse, which we denote by a to the minus 1, is a number that is going to satisfy a times a to the minus 1 equals 1 inside of Zn. Okay, now unlike additive inverses, sometimes these multiplicative inverses don't exist. All right, so our goal here is to compute A inverse for each A inside of Z8. So let's just start, all right? So 0 inverse, we would have to, that would have to be something that when multiplied by 0 equals 1, and that doesn't exist. One inverse, well, if I take 1 times 1, I get 1, which is what we want. So 1 inverse is equal to 1. 2 inverse, all right, so here's what I want you to do. Maybe pause the video and take every single thing in Z8 and multiply it by 2. Right? Start with 0 times 2, and then 1 times 2, 2 times 2, etc. You're never going to find anything in Z8 that multiplies by 2 in order to give 1, and therefore 2 inverse does not exist. Okay, so for 3 inverse, if I take 3 times itself, right, if I take 3 times 3, that will give me 9. If I divide 9 by 8, the remainder is 1. And so that means that 3 inverse is itself, right? And that's because 3 times 3 is equal to 1 in Z8. Okay, 4 inverse, you can convince yourself that that does not exist. 5 inverse. Okay. Well, you start off with 5 times 1, 5 times 2, 5 times 3, 5 times 4. 5 times 5 is 25, which is 1 more than a multiple of 8. So 5 is its own inverse. 6 inverse will not exist. You can check that. Take every single thing in Z8 and multiply by 6. You'll never get anything equal to 1. And then 7 inverse is just 7, right? If I take 7 times 7, I get 49, which is 1 more than a multiple of 8. Okay, so this is rather peculiar, right? There are some non-zero numbers in Z8 that do not have multiplicative inverses, and that's sort of bad behavior. Okay, now some of you who had Math 215, which is the mathematics discrete math course, you probably saw material on equivalence relations. In fact, you certainly saw material on equivalence relations. And you can define this equivalence relation, equivalence mod n, on the integers by saying that two integers are equivalent mod n if and only if their difference is divisible by k. So this equivalence relation gives us another way to think about this set Zn that we talked about and its arithmetic. So if a is an integer, we can let this a in brackets denote the equivalence class in the integers containing a. That is, it'll be a and all integers that are equivalent to a mod n. That is, a and all integers that differ from a by some multiple of n. So z sub n now can be regarded as this collection of equivalence classes, right? And it turns out that there are n minus 1 of them. And they can be represented by the numbers 0, 1, up through n minus 1. And further, you can define addition and multiplication on Zn just by, like if I have this equivalence class and I want it to add it to that equivalence class, I can just simply take the equivalence class that's represented by the ordinary integer sum a plus b. And the same thing for multiplication. So these notions of addition and multiplication are exactly analogous to the ones that we described on the previous slide. So a couple of slides ago, we noticed that there are non-zero elements in Z8 that fail to have a multiplicative inverse. Now, those problems will disappear if we look at ZP, where P is a prime number. So if P is prime, then ZP is what we call a field. Okay, that means it has a lot of nice arithmetic properties, and in particular, it means that every non-zero element is going to have a multiplicative inverse. Now, because ZP is a field when P is prime, we often write FP when we're referring to ZP. And that ought to look familiar because, back when we were talking about linear codes, we looked at the field F2, right? So that field F2 is exactly Z2 for the prime 2. All right, now here we have some linear equations that we're going to solve in various Zn's. And we'll see how this field structure benefits us a little bit. Okay, so we're supposed to first solve this linear equation 2x plus 6, or 2x equals 6, in F7. Okay, now how do we solve that? Well, what we could do maybe is multiply both sides of this equation on the left by the multiplicative inverse of 2. So in F7, the multiplicative inverse of 2 is 4, right? So here. So we're going to take 2 inverse times 2x equals 2 inverse times 6 Now, here we're working in F7, which is otherwise known as Z7, and 4 is the multiplicative inverse of 2 in Z7. So 4 times 2 is 8, which is 1 more than a multiple of 7. Now 4 times 6 is 24, and when we divide 24 by 7, we get a remainder of 3. So we get exactly one solution, and that's x equals 3. All right, and that's, what sort of what we expected to have happen. Now let's remain within Z7 and solve the equation 2x equals 5. So there, again, we have 2x equals 5. We multiply both sides by 2 inverse, which is the same as multiplying both sides by 4, right? Because 4 is the multiplicative inverse of 2 in F7. So that says that 1 times x is equal to 4 times 5. Well, 4 times 5 is 20. Divide by 7, the remainder is 6. So we get a single solution, x equals 6. Right, so far this is a yawner, right? I mean, we expected, okay, you have this linear equation, and we're able to solve it, and we get one solution. Well, the thing that is maybe lost on us here, if we don't think about it carefully, is that we're really using field properties, right? The existence of this multiplicative inverse of 2 forces there to be a single solution here. Okay, so now let's, so we've handled the first and the third bullet point equations. Let's now handle the second and fourth, where instead of working over Z7, we're going to work over Z8. We'll see how that affects us. Okay, so first let's get rid of all of this stuff. And go back. So now we're working over Z8. Now you might remember that we tried to find the multiplicative inverse of 2 in Z8, and it didn't exist, okay? So what can we do? Well, one thing we can do to try and find solutions of this equation is just plug in all the possible values. I mean, Z8 is a finite arithmetic, so we can plug in everything for x and see when we get 6 as a result. Well, we get 6, certainly. We don't get it when x equals 0, x equals 1 fails, x equals 2 fails. We do get it when x equals 3. X equals 4 will give us 0 again. X equals 5 would give us 2. X equals 6. 2 times 6 is 12. The remainder there upon division by 8 would be 4. But what about 2 times 7? 2 times 7 is 14. Divided by 8, the remainder is 6. So x equals 7 also works. So this is rather peculiar, right? When we're working over Z8, we have this linear equation. We expect one solution, but really there are two solutions, okay, which is peculiar. Now let's go down and try 2x equals 5. Okay, so I ask you now, maybe you want to pause the video and try plugging in every value of x in Z8. So that would mean plugging in x equals 0, x equals 1, x equals 2, up through x equals 7. And what you're going to find is that there is no solution. Okay, so the moral of this story is that there are real benefits to working real arithmetic benefits to working over a field like F7 as opposed to just some ordinary modular arithmetic like Z8. Now that we've addressed matters of arithmetic, we can begin to talk about cryptography. So we're going to introduce cryptography in the setting of Caesar's cryptosystem. So here I see that almost immediately I have misspelled Caesar's name. It should be C-A-E instead of C-E-A. So anyway, there's this Roman historian Suetonius who tells us about the lives of the Caesars. And one of the things that he relates is that Julius Caesar used an alphabet shift to encrypt messages. So the word encrypt means to take a sort of a plain text message, a message written in a natural alphabet, and then transform it into secret writing. So here's a modern interpretation of Caesar's cryptosystem. So what you do is you take the letters A, B, C, D, up through Z in order, and you identify those letters with the numbers 0, 1, 2, up through 25 in order. So that means that A corresponds to 0, B corresponds to 1, C corresponds to 2, and Z corresponds to 25. Now, in this cryptosystem, we're not going to worry about spaces or punctuation. They will be absent or unaffected for this application. Now, how do we do the alphabet shift? Well, in order to do that, we select a number in Z26. So notice that all these numbers 0, 1 through 25, those are all the elements of Z26. So we're going to choose a special element of Z26 called K. And this K is going to be called the key for our cryptosystem. So we can encrypt messages one symbol at a time using what's called an encryption function, which depends on K. And what it does is it takes a symbol which is identified with a number X, and then you just add K to X inside of Z26. All right, so here we have a task before us. We have Alice sending messages to Bob. So Alice wants to send the message spam is good to Bob in encrypted form, and we want to encrypt this message with K equals 13. So what I would recommend that you do before you try doing any encryption here is to write a little table like what I started here that gives all of the letters in the alphabet corresponding to their number in Z26. That will be a useful thing to have around. Okay, so the first thing we're going to do is to write out this message, spam is good. Which I happen to agree with, by the way. Whether you agree, that's up to you. Okay, now what we want to do is identify each one of those letters with a number, as we decided to do up here in item 1. So when we do that, this becomes letter 18. P is letter 15. A is letter 0. M is letter 12. Now we're ignoring spaces at the moment. I is letter 8. S is letter 18. G is letter 6. O is letter 14. And finally, D is going to be letter number 3. So these are our values of X. And now what we're going to do is compute E13 of X for each one of these. That is, we're going to take every single one of these numbers and add 13 to it inside of Z26. So first, when I take 18 plus 13, I get 31. but inside of Z26, that's equal to 5, right? Because if I take 31 divide by 26, the remainder is going to be 5. Okay, so I get 5 there. 15 plus 13 is 28, which is really 2 inside of Z26. 0 plus 13 is just 13. 12 plus 13 is 25. Okay, so we can keep doing this down the road. We can keep doing this. This becomes 21 and 5. And you can check my arithmetic here. And then 19, 14 and 13 is 27, which is 1 inside of Z26. And then we have 3 plus 13, which is 16. And so this message, if you now go up to this list of that corresponds or that identifies numbers with letters, letter number 5 is F. Letter number 2 is B. 13 is N. 25 is Z. And then we get VF. And then T, B, B, Q. All right, so this is the encrypted version using Caesar's cryptosystem where the key K is equal to 13. Okay, here again we see some information about Caesar's cryptosystem and paired again with this misspelling of Caesar in the top line, for which I apologize to Caesar. So again, we have the description of how it works, right? We identify letters A through Z with the numbers 0 through 25, regarded as elements of Z26. Spaces and other punctuation are ignored. We then select a key, an encryption key, which is a special element of Z26. And to encrypt a message one symbol at a time, what we do is we take a letter, we identify it with its appropriate number, X, and then we just add K to that number inside of Z26 to get the encryption. So here we have a couple of exercises involving decryption, right? That is how to take a piece of ciphertext, that is an encrypted message, and be able to know what the original message was. All right, so first bullet point, if K is the encryption key for Caesar's cryptosystem, then let's produce a rule for the decryption function. So if encryption takes a symbol and adds K, then decryption should take a ciphertext symbol and subtract K, right? So corresponding to this K, our decryption function, so d sub K of y ought to be y plus minus K. All right, now, well, let's suppose you don't know what K is and you're trying to figure it out. Like here, we have Alice sending Bob secret messages using the Caesar cryptosystem. And we have this third party, often called Eve, who's monitoring and wanting to figure out the messages that Alice is sending to Bob. Now, let's suppose that Eve is able to obtain this piece of ciphertext. The question is, what is the encryption key? So maybe this would be a good time to go away and see if you can figure out what it is. Okay, well, maybe you've gone away and you've tried to figure it out. Hopefully you have. So how would you do this? Well, one way to handle a problem like this is to look at the method of exhaustion. There are only 25 possible keys, So you could try all of them. And in fact, what you might discover is that this, D sub k, decryption of applied to some, number y would be y plus minus 10, which is equal to y plus 16. Okay, so that means that the encryption key, right? This is minus k here, and so that means that the value of k, the encryption key, is equal to 10. Now you might be wondering, well, what is the message that corresponds to that ciphertext? Well, maybe you've already figured out that it's brainwash. Okay, at any rate, this attack, what's called an attack by Eve on this cryptosystem, can be effectively undertaken by using this method of exhaustion, just trying all the keys until you get a potential plain text message that makes sense, right? This is going to be the only one that makes sense, this brainwash. Okay. We can generalize some of the notions that we've been talking about in the specific instance of the Caesar's cryptosystem. So here we let M and C be sets of messages, and we'll let K just be a set. If for each little k in K there's an injective function, that is a one-to-one function, E sub k from M to C, then we say that this collection of functions is a set of encryption functions. So these are things that are going to take ordinary messages in natural language and produce ciphertext, that is, secret messages in the set C. So this element K in capital K is called a key. Now, if we have a set of encryption functions, then the set of functions D sub L is called a set of decryption functions for these encryption functions. If for each K in capital K, there's an L also in capital K, so that D sub L of E sub K of M is just M again. So D sub L acts as an inverse on E sub K. Right? And that sort of makes sense, right? You start with your natural message M, you apply E sub K to M to get your secret writing, and then you apply D sub L to your secret writing to come back to the original message. Right, so that's how Bob and Alice will communicate with each other. Now we have an attacker, Eve, and one thing that we're always going to assume about Eve, and this is makes sense from the long history of cryptography, is we should always assume that Eve knows the method of encryption that's being used, right? She's going to know, for instance, that it's Caesar's cipher or Caesar's cryptosystem or whatever, but we assume that she does not know a priori the key that is being used. So really the key is the only thing that's assumed to be secret to Eve. Eve, we assume, knows the cryptosystem that's being used. One way to prevent an attack by exhaustion with the Caesar's cryptosystem is to allow more general permutations of the alphabet. So for instance, let's consider just any permutation, call it sigma, of the space character and the letters of the alphabet that fixes the space character. We can encrypt messages by taking a letter and just applying the permutation to that letter. Now, a permutation, you might remember, is simply a one-to-one and on-to function from this set of objects to itself. Now, the Caesar's cryptosystem involves a special class of permutations. In fact, there are 26 of them altogether if you count the do-nothing permutation, right? The one that just doesn't do anything at all. But if you look at general permutations, not just the ones of the type in the Caesar cipher, there are not just 26 of them, there are 26 factorial of them. So that is an enormous number of keys there. And so it's not feasible, really, to go through and check every single one of those keys. All right, so we're going to do an example of this new type of cryptosystem using the keyword gourmand. And we're going to use this keyword to help us encrypt the message Premier League. All right, so first of all, we need to figure out, well, what permutation sigma is determined by the keyword gourmand. So here's how we're going to figure that out. So we start our list of alphabet, right? So we're going to take A, B, C, D. This is going to be painful, guys. E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So those are our letters of the alphabet. Now we're not worrying about the space character because it's being sent to itself. So this is sort of our, plain text stuff over here. And now we're going to figure out a permutation of these letters based on the keyword gourmand. So what we're going to do is to write the letters for gourmand here at the very beginning. So this means plain text symbol A will go to ciphertext symbol G. Plain text symbol B will go to ciphertext symbol O, and so on. Okay, so you can see that it's rather important that the word gourmand not have any repeated letters, because if there were repeated letters, then you would have two distinct letters in your original alphabet that are encrypted to sort of the same letter in the ciphertext. So that's, for instance, why the keyword banana would be a bad keyword to use, because you would have multiple distinct symbols in the plain text that go to the same ciphertext symbol. That would be bad for decoding. Okay, so there's gourmand. Now, how do we fill out the rest of this? Well, we need to figure out where I gets sent. So I is going to get sent to the first letter that does not appear in gourmand. So that would be the letter B. J now will be the next, assigned to the next letter that is not already used. So we've already used A and B. We have not used C. K then we would want to assign to D, but we have already used D. So we need to assign it to E. L can be assigned to F. M cannot be assigned to G because G has already been used, but H has not. N can be assigned to I. O can be assigned to J. P can be assigned to K. Q to L. Now, R cannot be assigned to M because we've used M, but it can be assigned to P, S to Q. T cannot go to R, so it must go to S. U would go to T. And then V, W, X, Y, and Z are sent to themselves. So sigma, our permutation, takes the top row of symbols to the bottom row of symbols. So now we want to encrypt the message Premier League, and in fact, we're just going to do the word Premier here. And I'll let you figure out how to encrypt the word league. So it encrypts as this: K, P, M, H, B, M. Let's see, R goes to P. And then E goes to where? E goes to M. Right, so you can check and make sure I did this right. And then go on and compute the encryption of the word league. The permutation cryptosystem that we discussed on the previous slide might not be subject to attack by exhaustion, but it is subject to attack by something called frequency analysis. So let's suppose our attacker, Eve, intercepts a lot of ciphertext. Right? Maybe she intercepts a whole bunch of this stuff, and she notices that these particular letters, B, A, W, X, 0, Z, Q, and T, occur with these frequencies listed below out of 1,000 symbols. Then, what if she knows that the cryptosystem is one of these permutation cryptosystems, which is our assumption about the attacker Eve, right? That she knows what the cryptosystem is, but doesn't know the key. What she can do is look at frequency tables for the English language to help figure out what the key is, or what the ciphertext messages are. So our author in figure 10.1 in the book gives us a frequency table for letters in natural English, including the space symbol, out of 10,000 characters. Now, you can take that table together with this information and attempt to figure out what this piece of ciphertext is. So maybe you want to go away and see if you can fill in what it is. Okay, well, maybe you've paused the video and gone away and tried to decode this. So the decryption of this message is no man. Is an island. Okay, so what we've learned is that the Caesar system and its friend, the permutation cryptosystem, both of these are subject to relatively simple attack strategies by Eve. Right? The first one, the Caesar's cryptosystem, can be attacked by exhaustion. The permutation cryptosystem can be attacked successfully by frequency analysis. So we'll want to be able to develop cryptosystems that are not subject to such attacks.